Here are your notes 5.5, two objectives. Be able to factor polynomials in quadratic form and be able to solve polynomial equations by factoring. So the first one, we learned about factoring last section, factoring higher degree polynomials. This one, it's not really a pattern. You're basically, what you're going to do is you're going to turn higher degree polynomials into things that look like quadratics. That way, anything that we used for factoring quadratics, you can then use for um, that new form of the higher degree polynomial. Okay, so basically this one's transforming and then factoring. This one, right after we're done with this one, I'm going to go over how to solve polynomial equations using all the different factoring things that we've used in the past. Okay, so first off, quadratic versus quadratic form. So quadratic is a polynomial that has degree 2. So the highest exponent that you should have is its squared. So I put this little thing on the bottom for a reason, because basically x, this is a quadratic because there's a base that's being squared. So the base right now is just a regular old x. So inside of these blank spots, I'm going to put an x, because x is being squared. And if you think about this one, it's like this to the first power. So then we have x to the first power, that's our linear term. So we have a quadratic term because it's something being squared, and then we have a linear term because it's that same something to the first power. Now after that, you can factor this. X times x is x squared, 10 is a 1 times a 10, and a 2 times a 5. This does not meet any patterns that we learned in the past, so we're just going to do the guess and check. So since the front term is just an x squared, you can put an x here and an x here, because that's the only way to get an x squared. And then this back term is going to be the 2 and the 5, because that makes your 7. So 2 and 5 both being added, and then it's factored. So the whole point of showing this was a review of how to factor a quadratic. Now, quadratic form is not, I mean, as you can see, this expression right here is not a quadratic. It's quadratic form, though. Quadratic, it can be quadratic form because we can rewrite it to resemble a degree 2 polynomial. So in order to do that, what you need to do is this. First, I'm going to take this little model thing and put it underneath here, because I picked the numbers exactly the same as here. The only thing that's different are these 6 and the 3. So to make it in quadratic form, we need a squared part, and you don't necessarily need a linear part, but you need a squared part at least. So if I think about this, x to the 6th, could I rewrite this as a square? That way it looks like a polynomial of degree 2. And turns out I can, as long as you write it x to the 3rd. Because then using the power of a power, 3 times 2 is at 6. So this is the same thing. Now the linear term, if I look right here, this is actually going to be, now if you remember on this one, the linear term matched the squared term. So, because this was x, that was x also. So this one we got x cubed, so this other one's going to be an x cubed also, which matches right above. And there you go, because that's x cubed to the first power. So we have this, I'm just going to call this a thing. We have this thing squared, and that exact same thing to the first power. And that fits this same kind of model here to factor. So in order to factor this, you can use the same methods that we use to do quadratics. Now with the quadratic, this front term, we got to find the factors of this. So the only way we can get x to the 6th is if we do x to the 3rd times another x to the 3rd. So this must be x to the 3rd. This must be another x to the 3rd. All right. And then this other part's the part we need to find out, and we're going to find that out the exact same way we did over here with a 10, and it's going to be a 2 and a 5 again because that's the way I picked the numbers. So a 2 and a 5, both addition, and you're done. Okay. You might be able to factor some more sometimes, but not in this case. The only way we know how to factor a cube, if there's nothing that comes out of both, is by the sum or difference of cubes, and this does not fit that requirement, so we are done. All right, so every time you factor, try to look again and see if it fits another type of thing. All right, so that's it. So we're turning higher degree polynomials. You just factored a 6th degree polynomial, by the way, so good job. And the method of doing that is make it, if you can, because you're not always going to be able to do this, but if you can, make it into a quadratic form, and then use any of the methods, any of the patterns that we've used in the past to solve that quadratic form. Or not to solve it, to factor it, sorry. All right, so let's try these. So first off, this one looks it is a higher degree polynomial. It's the fourth power, so it's not a quadratic. So we don't know any rules for factoring quadratics. I'm sorry, fourth powers, quartics. But this does look like I could turn this into a squared pattern. So I could do this one of two ways. The way I'm going to do it is, I notice this is a difference of two squares. So I can turn this into, I'm just going to do the whole thing. 9x squared squared, that's 81x to the fourth, minus a 4 squared. That is a difference of two squares, which is a pattern, a quadratic pattern. Difference of two squares states that if you have a squared minus b squared, then that's a plus b times a minus b. So we're going to have our a part is a 9x squared plus 2, because, I'm sorry, not 2, that's a 4. Because it's the part that's being squared. The part that's being squared is a 4. Basically, that's your a part, that's your b part. So it's a plus b and a, whoops, I didn't write a. A is a 9x squared minus 4. All right, so I use the difference of squares to factor down to here. Now, keep in mind, you're supposed to keep looking. So right here, we have perfect squares front and back, but there's no such thing as a pattern of the sum of two squares. This actually is not factorable anymore to the way that we want it to look. This is a difference of two squares again. So this is a 3x being squared, and this is a 2 being squared. So you can leave this alone, 9x squared plus a 4. And this side, difference of squares again, you get two binomials, that's a plus b, so 3x plus 2, and a minus b, so 3x minus 2, and that is it. You are done. Okay, so that's the pattern there. You're basically just trying to look for things that make it look like things we've done in the past. So we've done this in the past. We made it look like the difference of two squares. Okay, this one. So first off, let's try to see if we can make it into some type of quadratic form. Front and back are not perfect squares, so I can't do any type of patterns here. Nothing comes out of the entire thing. So what I'm going to do is I'm going to look at this and try to turn it into a quadratic form. 2 is not a perfect square, so I'm just going to leave 2 alone. X to the fourth, I can turn that into a squared, but not like that. So x squared squared plus 11, and then you're going to have something to the first power, and that's going to be the x squared plus a 5. Okay, so that's how you would write that. You know what? Let me redo that. It's the right answer, so don't erase your page. 2 times something squared plus 11 times something to the first power plus that 5. That's our trinomial pattern of a quadratic normally. And the parts that are going to go inside of here are an x squared, another x squared, and that's it. Now in class I showed you guys a little bit of a trick here. If you're able to write here, and then now we have to do guess and check to factor this one. But once you get to here, it looks a little bit weird because we have all these x squared stuff going on. So what you can do is a method called they use it in calculus. It's called U substitution. They do it whenever something gets really complex and you want to make it look a little bit more simple. So in this case, it's not too bad, but I'll go ahead and show you. So what you can do is you can define your x squared. So I want to call anywhere I see an x squared a y. So anywhere I see an x squared, I'm going to replace it with a y. So you can put 2, whoops, no parentheses. This will turn into 2y squared plus 11y plus a 5. Now that should look more familiar because this goes back to the quadratic section, and then you just factor it the way you normally would. So this would be a 2y, a y, and then 5 and a 1. So let's see here. 5 should go here, 1 should go here. Yep, both plus. And then once you get to that point, you're done factoring. There's no other patterns or anything we can use. But the thing is now that we figured it out, we need to put this x squared back in because that's what the original problem was. So that y was just to help you kind of see it more clearly. So this will be a 2x squared plus 1 and an x squared plus a 5. Now, if you don't need to do this step. If you guys can see it from here, you can go directly down to here. Okay, that little step in the middle is just to clarify in case all these squares and squares start mixing you up. All right, this one was you do in class, so you guys can try that one on your own. All right, so now I want to make this connection for you guys. So far, we're going to start graphing this. Now, part of graphing is that you have to find the x-intercept. So it turns out if you have a polynomial like this and you end up solving it, putting this equal to 0, I've been over this with you guys a lot, it means that you're finding the x-intercept. So right now I want to show you what this graph looks like. Now this is a pretty good calculator. It's free online. Brings up something like this. Okay. You can type in whatever you want and then it'll graph it for you. So right now, just looking at this, I can see that it's a fifth power. We went over n behaviors. So the fifth power means the left side goes down and the right side goes up. So that's all we know so far. Now we're going to get into solving this. Once we solve it, we're going to find the x-intercepts. But now just to show you what the graph will look like though, so y equals 2x to the fifth minus 14x plus, x cubed plus 24x. Let me maximize this screen. And this is what the graph actually looks like. All right. Let's see here. That there is a setting for projector. Nope. Okay. Anyways, this is what the graph looks like. So as you can tell, it has a lot of ups and downs. We'll figure out how to do all these later on in this class. But for right now, like we said, we know the end behavior was the left side keeps going down, and it does, and the right side keeps going up. Now, like I told you before, we don't know what the stuff in the inside does. But what we're about to do is we're going to start solving this, which will tell us the x-intercepts, which are here, here. So it actually tells us on here. This nice thing about this. So it turns out our x-intercepts on this are -2, -1.732, 0, +1.732, and a 2. So we have 5 intercepts. Turns out it's a fifth power, and we're going to go over the connection with that tomorrow. So basically what we're going to have by the end of this class, or this notes today, is that we'll know the end behaviors, and then we'll know these x-intercepts. And then we'll figure all the rest out as we move on through the class. All right, so pretty funky looking graph. Go ahead and play around with this tool. It's pretty easy to figure out, and it's kind of cool because you can type in whatever you want. So for example, if I want to turn this into an inequality, bam, there it is. And it's dashed and shaded below. You can make it greater than, and it goes on the other side. So yeah, you can play around with it and then figure out by way of functions over here. But that's besides the point. I digress. All right, so we actually know the intercepts. Let's go ahead and do this for the first problem. Same problem, so y equals this, but we're going to be solving it, so we're going to set one side equal to 0, and let's go ahead and solve this out. So what we're going to do, since directions say by factoring, we're going to factor first. Now looking at this, we can actually factor. Whenever you're supposed to be factoring, you should try to figure out if you have a monomial you can pull out. So this one has 3 terms. All 3 of those terms I can pull a 2 out of all of the coefficients. So I can pull a 2 out. Now looking at the variable, I can also take an x out of all of these terms, but only one of them. So x. And now I am left with, let's see here, x to the 4th power minus 14x squared. Oh, that's not a 14. That's a 7. Aha, okay. Plus 12. All right. Now, this does look like not a pattern. That's not a perfect square right here. But this does look like a trinomial. It is a 4th power, so we're going to go ahead and try to turn it into a, hold on, something squared minus 7 times that something plus 12. So this will be x to the 2nd power, x to the 2nd. So 2x. And it's going to be x squared times another x squared. And then what makes it 12? They should both be negatives, because the only way you can get a negative times a negative to make this positive and still have a negative when you do the middle term. Looks like a 3 and a 4 equals 0. Now, at this point, you could actually, once you get down to squares, you could do one of two things. You can start splitting it apart using the zero product property, which states that when you have things being multiplied and they're equal to zero, that means that each of those things could be a zero. So I can set this as 2x equals 0, x squared minus 3 equals 0, and x squared minus 4 equals 0. So at this point, you could do that. Another thing you can do is you could actually keep factoring this one, and then you'll still end up with the same answer. But at this point, I'm going to go ahead and split them apart. So this will be a 2x equals 0, x squared minus 3 equals 0, or an x squared minus 4 equals 0. Now you just solve all three of those. So this is x equals 0. This is x squared equals 3. Square root both sides, so x equals, so square root, and then that's a plus or minus. So positive square root of 3, x equals negative square root of 3. And last one is x squared equals a 4, square root both sides, that's a plus minus. So x equals 2 and x equals negative 2. 5 roots. Square root of negative 3, just to kind of show you this, or square root of 3. So 3, blah, 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 square root 1.73. So this is approximately 1.73. Approximately negative 1.73. Those are the zeros of our graph. And let's bring this back up, see if it matches. Zoom in, too far in, zoom back out. Negative 2 and 2, negative 2 and 2, 1.73 and negative 1.73. Negative 1.73, negative positive 1.73, so those two are there, and your 0. And your 0. So that worked out nice and neat. There you go. You just found all of your x-intercepts of a 5th degree polynomial. So we know it goes down to the left, up to the right. We know all the zeros. So far, what we know about this graph is down to the left, up to the right, and all the zeros. So tomorrow we're going to figure out how to figure out the parts in between. But before that, let's go ahead and do one more example. Let me figure this out because I gotta look at your homework and see which one looks like them. All right, I'm gonna go ahead and show, because since I did one like this already, you can do it similar to this one. This one, you're gonna subtract 9x, you're gonna do factor by grouping once this is over here. But I do want to show this one. Actually, I'll show both. Never mind, I keep going back and forth. So minus 9x, minus 9x. Because I got to get one side equal to 0. So this will be x cubed minus 2x squared minus your 9x plus your 18 equals 0. 4 terms. Only way I know how to factor 4 terms, if nothing comes out, no monomial comes out of everything, so think about factor by grouping. So I'm going to group the first two, x cubed minus 2x squared, plus the group of the back two, which is a negative 9x plus an 18 equals 0. You cannot use a zero product property because this is not a product, this is a sum, and there's no such thing as a zero sum property. So what we're going to do here is we're going to take this and factor it. I can take an x squared out of there. I'll have an x minus a 2. Using factor by grouping, this should be an x minus 2. Only way to do that is if a negative 9 comes out. Double check that. Negative 9 times x is negative 9x. Negative 9 times negative 2 is a positive 18 equals 0. All right. Two groups are the same, so I'm going to pull them out front. X minus 2, x squared minus 9 equals 0. This is now another pattern, quadratic pattern, difference of squares. So you're going to do x minus 2, x plus 3, and an x minus 3 equals 0. At this point, I'm okay with you guys not splitting it apart since I've already tested you on the zero product property during quadratics. So if you can do this in your head, that's fine. They're all one-step equations. So x minus 2 equals 0, x plus 3 equals 0, x minus 3 equals 0. I am going to show this out in the notes, though. All right. And now solve all of them. You get x equals 2, or x equals -3, or x equals +3. All right. Those are your zeros. They call them zeros sometimes of this equation. All right. Some of your problems, actually all of the ones at the bottom, say find the real number solutions, which means that if you get an imaginary part, then I don't want that part. I just want the real parts. So with this one, there is a way to do this without factoring, but since it says to factor, you need to factor. All right. The way to do it is subtract 27 and take a cube root, but the directions say factoring. So on your homework tonight, I do want you guys factoring. By the way, homework tonight is not due until Monday. So I'll say that again towards the end in case somebody fast forwarded through this. But homework tonight is not due until Monday once again. We still have our quiz tomorrow, so it would help if you practice them, but there's a lot of problems on there, so I'm not going to make the entire thing due until Monday. All right, now this is a sum of cubes. So sum of cubes, this is just an x, that's a 3. This is an x cubed, this is a 3 cubed. So sum of cubes can be factored into a binomial along with a trinomial using a pattern that we've learned. That pattern is A, B. This is your A, this is your B. And then A squared, so x squared, and then AB, so 3x, and then B squared, which is 9. To figure out the signs, use your soap. Soap it up. So same, opposite, always positive. Same sign as this. Opposite sign of this, and then this one's always positive. All right, now we can split this into two. It's a quadratic now. Anytime we get it down to quadratic, go ahead and feel free to use the zero product property. So this is going to be an x plus 3 equals 0, and an x squared minus 3x plus 9 equals 0. So x equals -3. Now this side, let's try to factor it. You can't, because 9 is a 1 and a 9, and a 3 and a 3. And there's no way to get those together to make this -3 right here. So I can't factor it. So maybe we can do the quadratic formula. But before you do the quadratic formula, hopefully some of you guys remember the discriminant. Discriminant was b squared minus 4ac. What that told us is how many answers and what type we get. So if I actually use the discriminant right now, I can figure out, is this going to be imaginary? Because if it's imaginary, I don't got to worry about it, because the directions say find the real number. Now, if it didn't say that, you would actually have to solve this out, and then if you got imaginary numbers, that was part of your answers, or complex numbers would be part of your answer. But let's try this first. So b squared minus 4ac. Your b is a -3, minus 4. Your a is a 1. Your c is a 9. So looking at that, I can already tell this part's going to be bigger, and you're subtracting. So 9 is going to be, what's that? 9, 18, 27, 36. And that is a negative 27. So when you have a negative discriminant, that means you have two imaginary solutions. So I don't even have to worry about this part because I know it's going to be imaginary. So your only answer here that's real is x equals -3. All right. But keep in mind, if that does not say real, you'd actually have to solve this quadratic out just using methods that we've used in the past. Okay, and that's it. And like I said before, your homework that I gave you today, which is 5.5 homework, is not due until Monday. But make sure you guys are ready for the quiz. The quiz will cover everything from 5.1 up to 5.5. Okay, and if you have questions, feel free to write it in the comments. And if I don't answer it, then too bad. Okay, bye-bye. Bye.